So, welcome to this lecture. In the previous lecture, we saw that GL and R plus is path connected. So, let us begin this lecture by showing that proposition GL and C is path connected. So, to show that GL and C is path connected, so given a matrix A in GL and C, we will find a path joining A to identity. So, we have to find a path in GL and C. So, let us just look at this straight line path. So, let us consider this gamma t, this is t times identity plus 1 minus t times A. Okay. So, now note that if t is a complex number, then gamma t is actually a matrix in. So, this In is n times n identity matrix. Then gamma t is a matrix in M and C. It is an n cross n matrix with complex entries, right. So, what we need, we need to find, okay, so and note that gamma of 0 is equal to A and gamma of 1 is equal to identity. So, let P of t be equal to determinant of gamma of t. Okay. So, then this is a polynomial. So, this is a non-zero polynomial with coefficients in complex numbers, right. And this polynomial is non-zero because non-zero as P of 0 is equal to determinant of gamma of, okay, let's look at 1, or even gamma of 0 is fine, but gamma of 0 we know is A, which is not equal to 0 because A is in GL and C, right. So, thus P of t has at most finitely many roots, has at most n roots, right, since degree of P of t is less than or equal to n, right. So, if you make the complex plane, then here we have 0 and here we have 1, and let us say the roots of P are lambda 1 up to some lambda r, where r is less than or equal to n, right. So, this is lambda 1, lambda 2, lambda 3 up to lambda r, okay, and none of the lambda i's can be 0 or 1 because at P of 0 is determinant of A, which is non-zero, and P of 1 is determinant of identity, which is non-zero. Okay. So, we can simply take a path, joining 0 and 1 which misses all these lambda i's, yeah, in the complex plane. So, let S from 0, 1 to C be a continuous path such that S of 0 is equal to 0, S of 1 is equal to 1, and the gamma i's do not belong to the image of S. Okay. So then gamma compose S, this is from 0, 1 to M and C, the image lands in GL and C. Because if for any t as in 0, 1, the determinant of gamma of S of t is non-zero, as determinant of gamma of S of t is equal to P of S of t, which is non-zero, right? P of a complex number, P lambda is equal to 0 if and only if lambda is in the set lambda 1 up to lambda r. And the image of S misses all these lambda i's, so therefore the determinant is never 0. Yeah, thus gamma compose S from 0, 1, the image lands inside GL and C, and clearly gamma compose S of 0 is equal to gamma of 0, which is equal to A, and gamma compose S of 1 is equal to gamma of 1 is equal to identity, right? So thus every matrix A in GL and C can be joined to identity by a continuous path. In GL and C. So thus GL and C is path connected. So therefore, using this nice trick, we saw that GL and C is path connected, and this is much easier to prove than the case of GL and R plus. Okay. So let's make this simple observation. So this completes the proof. So lemma, let X be path connected and let F from X to Y be a continuous map. Okay, so then f of X contained in Y with the subspace topology is path connected. So let's see this. This is easy to prove. So recall that we had seen, and we have used it many times now, if we view F as a map from X to f of X, where f of X has the subspace topology, from Y, then F is continuous. Right. So now we want to show that f of X is path connected. So if we choose, so let f of X1 and f of X2 be any 2 points in f of X, right? So we have our X over here, and here we have X1 and X2, and here we have, let's say, f of X, this f of X1 and this is f of x2, right? So since x is path connected, there exists a path which joins x2, x1, right? And this is f. Since x is path connected, there exists gamma from 0, 1 to x such that gamma of 0 is x1 and gamma of 1 is x2, right? So this implies that f compose gamma from 0, 1 to f of x is a continuous path joining f of x1 and f of x2. So this implies that f of x is path connected. Okay, so this completes the proof. So as a corollary of this, we have if x is path connected and f from x to y is a surjective continuous map, then y is path connected. Right? This corollary is immediate because since f is surjective, it follows that y is equal to f of x, and now we just use the previous lemma. So as a corollary of this corollary, we have these nice applications. SL and R this n cross n matrices such that determinant of A is equal to 1 is path connected. Right. So in order to show that SL and R is path connected, all that we have to do is we have to construct, using the previous corollary, a surjective map from a path connected space to SL and R. So we will simply take this map to SL and R. So this map is, so if I take a matrix A, yeah, A gets mapped to, so this is A. So we just divide all the entries in the first column with determinant of A. And the other entries are as it is. Right. So let's call this map F, yeah. So clearly the image of F, okay, so determinant of F of A is equal to, since the first column has been scaled by 1 upon determinant of A, this is equal to 1 upon determinant of A into determinant of A, which is 1. Okay. Now SL and R is contained inside GL and R, and here we have F, GL and R plus, sorry, to SL and R, right? And this composition is equal to identity, right? So this implies that F is surjective, right? So it only remains to show that F is continuous, but that is easy to see because, so SL and R has the subspace topology from M and R. SL and R is a closed subspace of M and R, and it has a subspace topology, and therefore to show that F is continuous, it's enough to show that continuous if and only if I compose F is continuous. And to say that I composed f is continuous, it's enough to show that the coordinate functions are continuous. Yeah, but so to show I compose f is continuous, enough to show that the coordinate functions are continuous. Yeah, but what are the coordinate functions? So if we start with A, then the coordinate functions of I compose f of A. So in the first column, the entries are of this type: A I1 divided by determinant of A. Yeah, but 1 upon determinant of A is once again a continuous function. So since determinant does not vanish on GL and R plus, is continuous and non-zero, this implies the function A goes to 1 upon determinant of A is continuous, right? So this implies, if I take A and I send it to AI1 divided by determinant of A, this is continuous, right? And similarly, A goes to Aij, where j is strictly greater than 1, is also continuous, right? So thus the coordinate functions of I compose f are continuous. This implies I compose f is continuous. This implies f is continuous. Yeah, and since GL and R plus is path connected, and f is surjective and continuous, this implies SL and R is path connected. So this is one application. So similarly, we can also show that SL and C this n cross n matrix with complex entries such that determinant of A is equal to 1 is path connected. Right? Again, we use the same map from GL and C to SL and C, where we just scale the first column by 1 upon determinant of A. Okay, so we will end this lecture here, and in the next lecture we will talk about compactness.